Welcome back. This is video lecture 24.3, and we're going to talk about section 5 in chapter 24, where we're going to calculate the potential that is created by what's called a continuous charge distribution. And the key idea here is that we're finding the electric potential due to a distribution of charge that can't be treated as a single particle. We know how to calculate the potential created by a single particle. I'll draw it up here. There's a point particle. It's got a charge Q. You are sitting there at that point, distance r from that particle. The electric potential at that point is Q over 4 pi epsilon 0 little r, the distance you are from the charge. What that really is the potential difference due to the charge, between this point where you are and a reference point at infinity, where by definition the potential equals 0. Okay, now that's for a point charge. But what if we have something that can't be treated like a point charge? Something that's an extended body. We're going to start with a uniformly charged rod, maybe shaped like this pencil. And if we're at a point near this pencil, that doesn't look like a point particle, and you can't treat it as a single point particle. So the question is, how do you find the electric potential at a certain location from something shaped like this? And it's the same trick that you would use to find the electric field created by a distribution of charge like this. And the trick goes like this. Okay? We treat the distribution as consisting of an infinite number of charged point particles. We find the electric potential from each one of those point particles and add all those contributions up to get the total. But the good news is that electric potential is a scalar. So we're adding up a bunch of scalar quantities as opposed to vector quantities, and that's good. All right, so we're going to consider here a rod. It's got some total length, big L, and it has a uniform linear charge density, lambda, a charge per unit length in the SI unit of Coulomb per meter. And it's the same value of lambda everywhere along the rod. We are to calculate the electric potential, V, relative to infinity, meaning using the reference point at infinity, at the point they've marked with a P. And that point is a distance little d above one end of the rod. Now, there's no actual charge at point P. I'll mark it with an X. That's where we're sitting, at point P. And we want the total electric potential there, created by this uniformly charged rod. Now, to help us deal with the math of the calculation, notice what the picture does. It sets up the geometry for us. Look very carefully. It has placed the rod along the x-axis with its left end at the origin and its right end at x equals L. And then the point P is a perpendicular distance d above that left end, above the origin. If you want to think of point P as being on the y-axis, you're welcome to do so. Okay, so the trick again is to imagine breaking up this charged rod into an infinite number of infinitesimal pieces. Each one of those little pieces can be thought of as a point particle. Okay, so let's do that in our next picture. Our next picture shows one arbitrarily chosen of the very, very many little infinitesimal pieces of the rod. Okay, and if you look very carefully at the picture down here in the lower right, the little piece has been shaded a kind of an orange color. It's got a length dx along the rod and along the x-axis, and the center of that piece itself is a distance x from the origin, which is the left end. Then there's the distance d, that point P is above the left end, and then there is, and this is very important, the distance r from the highlighted point particle to point P. Please note from geometry that r in this picture is the square root of x squared plus d squared. Okay? All right, so we have selected an arbitrary differential element dx of the rod with an infinitesimal amount of charge, dq. Now we're now going to write down an expression for the contribution dv to the potential from this element. Well, treat it like a particle. There's the little highlighted element right there. That's a particle with charge dq. Okay, how much charge is that dq? Well, it's the charge peanut length of the rod, lambda, which is the same everywhere along the rod, times the length of the little piece, which is just dx. And now the contribution to the potential from this little piece, we'll call it dv, at point P, would be, now you get to treat that little piece as a point particle. So it's the charge of that little piece, dq, over 4 pi epsilon 0, and then r representing the distance from dq to point P. Then just write dq as lambda times dx, and write r as the square root of x squared plus d squared. And we've done our first big step. Okay? All right. Now there's really only one more step. Don't have to worry about components of potential, do we? Use the principle of superposition to sum all the contributions dV from all the charge elements along the rod. This summing is scalar addition. That's one of the reasons we even talk about electric potential, because it's scalar, and scalars are good to work with. This is scalar addition, and the result will give us the net electric potential at P due to the entire rod. So here we go. So V net at point P is what you get when you add up all the dVs from all the little pieces that make up the rod. And now we'll substitute our expression for dV, lambda dx over 4 pi epsilon 0 square root of x squared plus d squared, where I am to think of the variable x as ranging from, on the far left end, x equals 0, and on the far right end, x is equal to L, the length of the rod. So on my integral over dx, the lower limit will be x equals 0, and the upper limit will be x equals L. Now I've got to figure out what I can bring out front of the integral. That's always important. I'd like you to take just a moment and think about it for yourself. Pause the video, that's fine. Figure out what quantities can be brought out front of the integral. That's what you need to do. Okay, so did you figure out what can be brought out front? You can bring out the lambda. You see why? Because it's a uniform linear charge density. You can bring out the 1 over 4 pi epsilon 0. They're all constants. But you can't bring anything else out. You can't bring dx. You can never bring dx or dy or dz or whatever it is out front. Never. And then in the denominator, you got square root of x squared plus d squared, and you can't bring that out because it depends on x. And then the limits are from x going to 0, going from 0 to L. Now we're faced with an integral we have to do. And many of you are still learning techniques of integration. So I'm not going to belabor how you do it, okay? What I am going to point out is that you could look up this integral. It's integral 17 in Appendix E on Wiley Plus in the math appendix, okay? It's integral number 17. And it turns out to be a natural logarithm because it's got a dx upstairs and it's got a square root of x squared, so that's like x to the 1 power downstairs, and that's how you get a log. But it's a little more complicated than that. So we get, when we look up that integral 17 in Appendix E on Wiley Plus, don't forget the lambda over 4 pi epsilon 0, we get natural log of x plus square root of x squared plus d squared. And then we put in the limits for x from 0 to L. We better do those limits carefully. So we get v net equals lambda over 4 pi epsilon 0. Okay, for the upper limit, we substitute in x equals L inside the logarithm. So we'll have the log of L plus square root of L squared plus d squared. Then minus, and now we'll substitute in x equals 0 inside the logarithm. You see that's going to simplify to, all you're going to have left inside the logarithm is the square root of d squared, which is just d. Now what most people would do at this point is use the property of logarithms that log of a, I'll write it over here to the side, minus the log of b is equal to the log of a over b. So I can then use that to simplify this to the log of L plus square root of L squared plus d squared all over d. And we have found the electric potential. Now let's be clear what we've done. We've got a rod. It's got a total length L. It's got a uniform charge per unit length, lambda, along it. And we have gone perpendicularly upward above one end to a point that is a distance d above the end. If that's what we're doing, then we can use this formula right here, and we have calculated the electric potential at that location for such a charged rod. Then you can plug in the lambda that's given and the L and the D. Now, note something about that lambda. It could be that the way they tell you that is indirectly in a problem. They could tell you that the rod has some length L and some total charge, say, big Q, distributed uniformly along its length. Then you would just note that lambda would be the total charge of the thing over its total length. And then you could still use this formula. Okay? Note that inside the logarithm, the numerator is larger than the denominator. So I'm taking the log of a number bigger than 1. So I know this result's going to be positive if lambda is positive. Right? If the charge that's smeared out uniformly along the rod is positive, then that would make the lambda positive. You could have a negatively charged rod. Then the lambda would be a negative number. Then the V net would be a negative number because of the lambda there. Okay? All right, so the point is, this is how you tackle this kind of problem. Finding the electric potential of a continuous charge distribution, we started with a linear charge distribution. Now, one thing that you have to realize is this is specialized to this kind of situation. We could give you a different situation where you have the uniformly charged rod of length L, and now you're going to take the perpendicular bisector, and you're some distance d above that. You can't use this formula then. You've got to work it out, what it is, doing this kind of integral like I did here. Okay? So I'm using this as an example to show you how you tackle this kind of one-dimensional charge distribution, finding the electric potential. Now let's do a two-dimensional distribution. How about a charged disk? A uniformly charged disk, right? For more practice. We now want to find the electric potential on the central axis. It's going to be V as a function of Z, of a uniformly charged disk of radius big R and uniform surface charge density sigma. So there's the picture. You can see the disk. It's got a radius big R, like that. The point P is on the central axis, height Z above the center. And that's where we are at the point marked with the X. And we want the net electric potential there at that point P. Okay? And again, you can't treat that as a particle. You have to instead break it up into infinitesimal pieces, find the electric potential of each such piece, and then add up all the contributions to get the total. Now, how you break it up into pieces is often a function of the shape of the thing. And since the thing is shaped as a disk, what turns out to be useful in this case is to select the tiny piece as being a very thin ring. So we select a thin ring as an arbitrary differential element of the disk. And that's now shown in the second picture. See how they shaded in kind of an orange? A thin ring. Okay? That's what we're going to do. It's got a radius, the ring does, S. It's got a thickness, ds. And it's just one of the many rings that you would need nested from the center out to the edge to make up the whole disk. But we've picked one of them arbitrarily, one of those rings. Notice that the distance from any point on that highlighted ring, they've drawn it from this left edge, but that distance is what they call little r. That's the distance from any point on the highlighted ring to point P where we are. Note that this distance from the center of the disk and the ring out to point P, they call z. Note from geometry that little r is the square root of s squared plus z squared. Just look at the right triangle there. That's important to see that. All right, so now that we've drawn a differential element, we've chosen a ring, we're going to write down an expression for the contribution dV to the potential at point P from this element, this ring. And probably the first thing we want to do is write down an expression for the charge of that ring. I'm going to call that amount of charge dq because it's an infinitesimal width. All right, now let's not overthink it. Don't make it too complicated. You can see the little ring there, it's shaded in orange. Remember, this disk in general has a uniform charge per unit area sigma all over its surface. So, to get the charge of that highlighted ring, I would take the sigma for the disk, the charge per unit area, and I would multiply it by the area of that highlighted ring, and I'm going to denote that dA ring. That's the area of the highlighted ring. Now don't overthink that term. What is the area of the highlighted ring? You go around once, that's the circumference, and it's got a little bit of width ds. So you take the circumference times ds. So we have sigma times. The circumference is 2 pi s. Don't say big R and don't say little r, because the radius of the ring is s, times the thickness of the ring, ds. Sigma times 2 pi s ds. And that's our dq. So our dv from just the ring, I'm going to add that subscript, is the dq of the ring over 4 pi epsilon 0 little r. Look at my picture over there on the right. Little r. Not big R, not S, not Z. You really have to look at this picture and think about it. Because what I need is I need here the R symbol right there. I need the distance from a point on the ring to where we are, and we are at point P. And every point on the ring is the distance little r that I've drawn from point P, and little r is the square root of s squared plus z squared. It's really vital that you see that. Okay? Now for the dq, we'll put in that expression you see up above. I'm going to write it like this. 2 pi sigma s times ds. And in the denominator, 4 pi epsilon 0. And for r, square root of s squared plus c squared. So there's our little contribution to the potential at point P from that highlighted ring. terms of the radius of the ring, S, its thickness, ds, and sigma. Note, by the way, that I can cancel the 2 pi and the 4 pi, leaving just a 2 downstairs. Might as well do that, simplify things. All right, now the next big step. Use the principle of superposition to add up to sum all the contributions dV from all the charge elements making up the disk. This is scalar addition and gives the net electric potential at P due to the disk. So V net is the sum of all the dV rings. So we have another integral to do. We have the integral of sigma S ds over 2 epsilon 0 square root of s squared plus z squared. Now we got to get the limits on the integral, right? It's a definite integral. Well, the variable of integration is s, ds. So the limits on the integral have to be s values. And we start at the center point, which corresponds to an s of 0, and we end when we're out at the outer edge, and that's an s of big R, because that would be the outermost ring at the very edge of the disk. Okay? Next, what symbols get to be brought out front? Think about that for a minute. Pause the video if you need to. That's fine. What symbols come out front of the integral? Okay, did you say that you can bring out the sigma upstairs and the 2 epsilon 0 downstairs? And that's it. And then inside the integral upstairs, you have an SDS. Downstairs, you have the square root of s squared plus z squared, where the limit goes from 0 to big R. Okay? S is the variable of integration. S is the variable that changes from 0 to big R as we look at successive rings. So anything that has an S cannot be brought out front. Now we're stuck with another integral to do. Right? Okay. Well, turns out this one can be done with a u substitution. So let's just go ahead and do it. Let u equal s squared plus z squared. Then du is 2s ds. I think of z as a constant as far as the integral is concerned, because for every ring, the particular distance labeled z is no different. It's the same for all of them. All right. So let's see what we get next after we do this substitution. V net equals sigma over 2 epsilon 0 times. Okay, now look, inside the integral, I have a factor SDS. And right down here, I have that SDS is equal to du over 2. So where I have SDS, I'm going to replace it with du over 2. I can bring that over 2 out front. And then I have du over the square root of u. And let's go ahead and change the limits to u values. What's the lower limit and the upper limit for the new variable u? Well, just remember the defining relationship for u is up there. And when the integral was with respect to s, the lower limit was 0, so we start at s equals 0. If we plug in s equals 0, the starting value for u is z squared. And the upper limit for s is big R, so we plug that into the u formula, and we get the upper limit for u is big R squared plus z squared. So this is sigma over 4 epsilon 0. I'm going to write it like this, u to the minus 1/2 power du from z squared to r squared plus z squared. And then I just think of that as integral as x to the n dx. Right? Look at the pattern where the n is negative 1/2. So the integral of x to the n dx is x to the n plus 1 over n plus 1. But n is minus 1/2. So n plus 1 is plus 1/2. So the result of the integral, we still have the sigma over 4 epsilon 0, is u to the 1/2, u to the plus 1/2, over 1/2. With the limits there. Okay, note that I can get some more cancellation. So I get a 2 there. So what do I have now? I have sigma over 2 epsilon 0, and now I plug in my limits. U to the 1/2, of course, means square root of u. Put in the upper limit, I've got square root of r squared plus z squared minus square root of z squared. Well, I'll write that as absolute value of z, because it's got to be, if you want the positive result. Okay? And now, here you are on the central axis of a disk. And you can use this to find the potential at any point on the central axis of the disk. You need to know 3 things. What's the charge per unit area of the disk, sigma? What's the radius of the disk, big R? And where are you on that z-axis, that perpendicular axis? All right, so we'll be talking about this approach in class for finding the potential of a continuous charge distribution. But one of the takeaways is, if you think way back to chapter 22 when we found the electric field of a continuous charge distribution, we had to do similar kind of thinking, but we had to deal with a vector quantity, so we had to worry about components. No components here to worry about, and that's what makes this easier. Okay, so just a little bit more practice for you to think about. This you can do for class engagement on Blackboard. Okay. Here's the first part. Consider a thin ring of radius r with total charge little q uniformly distributed around its circumference. Just a ring. Write down an expression for the potential V of z on the central axis of the ring at height z above its center. So in part A, what you have to imagine is that you have a ring. Okay? And then there's the center, and there's the z-axis going up. There you are at a point, height z. Okay. The ring has radius big R, total charge q. It's a ring, though, not a disk. It's got a hollow interior. Write down the formula for V of z. Now, don't overwork it. The answer for the V of a ring is right here on the screen. You just got to figure out how to express it correctly in this case, where the total charge of the ring is q, radius of the ring is big R, and you're at the point with distance z. Just write down the formula. There's no calculating to do. You just write it down. B, using your answer from A, write down an expression for the potential at z equals 0, which is the exact center of the ring. So now what we're saying is you're sitting right there at the very center of the ring. What's the expression for V? Notice how we would write it there, V at 0. Okay? All right, then part C is the following. Let's extend what you've learned in answering really A and B to now tackle the following situation. It involves the figures you see below. There are 3 arrangements of concentric circular arcs. They might be complete rings, they might only be part of a ring, but they're all circular arcs. Okay? In the arrangements, the outer arcs all have the same radius and the same charge plus q, the outer ones. The intermediate arcs have the same radius and the same charge, plus 2q. And the inner arcs have the same radius and the same charge, plus 0.5q. Right? So all inner arcs have the same radius, all middle arcs have the same radius, all outer arcs have the same radius. All inner arcs have charge plus 0.5q, All middle arcs have charge plus 2q, and all outer arcs have charge plus q. You need to basically get an expression for the net electric potential at the origin at z equals 0 for each of these arrangements, because you need to rank the arrangements according to the net potential at the origin. Greatest first. Okay? All right, so that's the task, and then we'll be talking in class more about the electric potential of a continuous charge distribution. That's all for this video.